Okay, it seems that there was a, when the connection was lost, please write a message in Telegram chat when the connection is lost, because I can't find this moment. What was the last moment when the connection was lost? Anyone, please help me.
You when you started to explain the problem to.
Okay, so we have one monkey. We have a English keyboard, only capitals letter. Let's consider only capitals letter. We have 26 letters, and tau will be the first moment of time. The monkey will type the word abracadabra. That's 4. That's 12 letters. So no. Abra, 4 letters. Cadabra. That's 11 letters. 11 letters. And let's say 1 key press per second. What is the expected value of tau? I propose 4 variants: 1 year, 10 years, 100 years, 1 million years. What is the expected value of time? And after you guess, we will try to solve this problem using martingale. There are no martingales in this problem, but the easiest solution I know is with martingales. Anyone who can guess what is the closest value to expected value of tau?
How often does it press the keys?
1 key press per second. 1 key press per second. Every second 1 new letter. Every second 1 new letter. One key press per second. So 60 letters in a minute. So that's a monkey.
Let's be 1,000,000 years.
How many years?
The last option.
The last option. Okay, now let's solve it. So I will construct. I will construct a martingale. I will construct a fair game. So let's organize a casino, and we will bet. We will create a fair game. We will bet on the next letter the monkey chooses. So okay, let's organize a fair game. So the art of martingale use is the art of creating martingales out of nothing. So there are no martingales at all in this problem, but we will create a martingale, a special martingale that will allow us to calculate expected value. So we will create a martingale. Create a martingale. We'll create a martingale. So let's organize a casino. So let's open a casino. We will open a casino. We have a queue of people, who are waiting to enter our casino. And let's imagine that every guy is with $1. Everyone who enters our casino brings $1. So we are creating the rules out of nothing. And for example, rule one of our casino. Rule 1: a player can enter with $1 only. So that's the rule 1 of our casino. Now, inside the casino, so why such a strange rule? Why such a strange rule? Imagine the total welfare of all the players inside the casino. So imagine the SN, the total welfare of all players, the total welfare of all players inside a casino after the entrance of n players. So Sn will be the total welfare of all players inside the casino after the entrance of n players. So if we organize a fair game, so our casino will be fair casino. So obviously expected value of Sn is n. Yeah. If each player brings $1 with him or with her, and we have a fair game inside. So if you bring $n into system, then the average welfare of all the players will be n. Okay, and hence we will consider the martingale, mn will be Sn minus n. So on average, if we subtract the number of money invested in the system, we have Sn, the total welfare of all players. We subtract the money invested. So basically this difference is this total gain of all players at time moment n. So that's the total profit of all players inside. So that's the total profit of all players inside inside the casino. We have the casino inside the casino after the entrance of n players. And hence now we are free. So now we have the martingale. So that will be a martingale. And now we are free to set up the rules of game to make our expected value calculation easy. So we will specify the rules in such a way that players will bet on the key, the monkey types, and we will do this in the simplest possible fashion. So imagine rule 2, at every moment of time, at every moment of time, each player inside casino bets all his money on the next letter. And imagine rule 3. So when every player bets on A, then on B, then on R, and so on. So on the letters of the word abracadabra. Yeah, the letters of the word abracadabra. So I will have only 3 rules. Each moment of time, so each moment, each second, each second, a player enters with $1. Sn, the total welfare of all players. The martingale is the total welfare minus n, because we have inflow of dollars in our casino. So to make this Sn a martingale, we need to subtract n. And rule 2, at every moment of time, every second, each player inside casino bets all his money on the next letter, and every player bets on A, then on B, then on R, then on A, then on C, letters of the word abracadabra. So let's imagine one possible history of the game, one possible.
Sorry, could you please show the definition of martingale just for a second?
There are two definitions of a martingale, one with sigma algebras, the other one without sigma algebras. The intuition, that's a fortune of a player in a fair game. One is expected value of the next one is current value, and with filtrations, expected value of the next xn plus 1 given current information is current welfare.
Thank you very much.
So in this game, you may think that the casino is a player. Yeah, the casino is a player, and normally as a casino, I have an inflow of dollars every moment of time. One more dollar is inside the casino, and to make the welfare of a casino, so basically Sn. So Sn is the welfare of players, and basically it is something minus welfare of the casino. Yeah, Sn grows on average, and so Mn, Sn minus n is constant on average, so that's a martingale. Okay, so imagine, so let's, to check whether everyone understands our rules, let's consider particular history. So let's consider particular history. So that will be moment t equal to 1, t equal to 2, t equal to 3, t equal to 4, t equal to 5, t equal to 6, t equal to 7. So player number 1, enters and bets A, B, C, D, oh, sorry, abra, ca, so on. Player number 2 will enter at the second moment of time, and he will bet on abracadabra. Player number 3 will enter at the first moment, at the third moment of time, and he will bet on abracadabra. 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 And so on. Every moment of time, we have new player who enters the casino. And imagine monkey. We have monkey. We have monkey. So monkey type B, X, R, C, W, C, W, A, B, N, and so on. And so we can, given the sequence of letters created by monkey, we can get the welfare of each player. Each player. So each player, he enters with $1. So initially, each player has $1. So at T0, player 1 has $1. He bets on A, but the monkey types B, so he will get $0. Yeah, 0. And because he has $0, he has $0. Okay. Player number 2, he has $1 before entering the casino, He enters the casino, bets on A, but the monkey types X. Oops, the second player is unhappy. He loses his money when he enters the casino, and he is sitting sad, without money, looking at the monkey. The third player, before entering the casino, he has $1. He bets on A, but the monkey types R. And so the third player is sitting sad, looking at the monkey without dollars. But if you consider the player number 4, number 5, number 6, if you consider player number 6, yeah, he enters our casino at time moment 6, and the game is more interesting for him. Yeah, he enters with $1 before betting. He has $1. After guessing the letter, he has $26. Yeah, we have a fair game. Yeah, because chances of guessing are 1 over 26. Yeah, because there are 26 letters in English alphabet. So if you guess the letter, your fortune is multiplied by 26 to make the game fair. Yet to have a martingale, we need to multiply the bet by 26. Okay, so he has $26. He bets on B. He bets on B, $26. And the monkey types B. So how much money the player 6 has after the second bet? How much money here? To make the game fair, if you have 1 over 26 chances, probability of guessing is 1 over 26. So to make the game fair, we need to multiply
20 squared.
Yeah. 26 squared. Yeah.
Squared.
Yeah, that's okay. And then he loses everything. And he's very sad. Okay, so these are the rules of the game. And now let's see how this solves, how this strange martingale created out of nothing solves our problem. Okay, let's imagine the final moment of time when monkey types finally. There will be moment of time t equal to tau when our casino is closed. The monkey has typed abracadabra. So, monkey. So that's the first moment in the history. Then the monkey has typed abracadabra. Okay. So now let's consider the welfare of players in our casino. The player who entered at the last moment of time, player number tau, according to our rules of the casino, he bets on A, and the fortune, and he has fortune $26. Now let's consider player T minus 1, player tau minus 1, sorry, player tau minus 1. He enters at the moment tau minus 1, he bets on A, he bets on B here, and his fortune is, he loses everything at the first bet, and his fortune is 0, because he lost everything on the first bet. Okay, are there any players who are in the money? Are there any other players who are in the money?
The one who entered when abracadabra started.
Yeah, that guy is very rich. Yeah, there is a very happy guy. there is a very happy guy, but not only. Yeah, this guy is very rich. It has 26 to the power 11. Yeah, this guy is very rich. But there is one more guy who is in the money.
Also Abra.
Yeah, there is a guy who arrived here, Abra, and this guy is very happy too because it has 26 power 4 fortune, and the other guys are fed, and they have nothing. Yeah. Okay. So as tau is 26 to 11 plus 26 to 4 plus 26 to 1. That is a value.
Sorry.
Yeah.
It feels like there is one more guy with money. Don't know if it matters or not, but if we imagine some guy starts. Well, I just thought
Tau
maybe
is the
we could
first
also
moment.
place abracadabra like before this
No,
letter.
Tau is the first moment. Tau is the first moment of appearance of abracadabra. So Tau is the first moment of appearance of abracadabra. There are no abracadabra before Tau.
Okay, I get it now. Yes,
So Tau
thank you
is
very
the
much.
first moment, yeah?
Thank you very much.
So you can have abracada XWZ. You can have abracadab P and Q, but you can't have abracadabra before Tau. Tau is the moment of time. So by definition, we said that Tau first moment of time. So there are many players who have lost all their money. Yes. Okay. So let's continue. So that is S Tau. M Tau is so what is Mn? Mn is Sn minus n. So we subtracted n to create a martingale. So what is M Tau? M Tau is S Tau minus Tau. Hence, M Tau is 26 power 11 plus 26 power 4 plus 26 to 1. Well, Mn is a martingale. Mn is a martingale. Tau is a stopping time. Hence, according to Dup's theorem, expected value of M Tau, I will not check the technical details now. I can check the technical assumption. There is a technical mathematical assumption in this theorem. I will not check this, but believe me, we can check technical assumptions. Okay, expected value of M Tau is M0. M0 is S0 minus 0. The number of players before the casino opens is 0. So we have $0. Hence, expected value of 26 power 11 plus 26 power 4 plus 26 1 minus tau is 0. Yoo-hoo! Out of nothing. The expected value of tau is 26 to 11 plus 26 to 4 plus 26 to 1. So that's the value we need. Yeah. So that's expected number of. So that's in seconds. Yeah, that's seconds. And that's the craft, the magic. We can, in many problems, we can create a martingale to solve a problem. The problem itself has nothing to do with martingales. There are no martingales in the statement of this probability problem. There are no martingales. Tau, first moment of time, random variable, expected value of random variable. And to calculate expected value of random variable, I've created a martingale, and I have used Dup's theorem, and I have solved this problem. Okay, and this value is approximately, so that's value in seconds. It is roughly 3.6 times 10 to the 15 seconds. Yeah. Seconds. It has 16 digits. Yeah. And if we just count in years, yeah, if we just count in years this value, if we divide by 60, we get minutes. If we divide by 60, we get hours. If we divide by 24, we get days. If we divide by 365, we will get years, and it happens to be something like this is approximately let me check on the calculator. No, it is if I divide, so if I go to years, it is 116385860. So it's 116 million years. To type abracadabra.
And so monkey is typing like 1 word per second?
1 letter per second.
Yes, 1 letter.
Okay, let's consider another problem.
So can I like clarify to find some stopping time of a random process? We just need to like formulate it in sense of martingale, and like maybe imagine that we have some casino with players.
Yeah. Okay, let's provide. I think we have 10 minutes more. Yeah, we have 10 minutes. Yeah, we have 10 minutes more. Let's study. I think this example is very beautiful. We create martingale out of nothing. Okay, let's consider another example. Let's consider the ordinary. So you play. So you imagine that you bet. Imagine that you can. So problem number 3. I think that it's a little bit easy. Yeah. Problem number 3. Imagine that we bet either on oh yeah. So let's imagine that we bet on red, or we bet on black, and imagine that there are no zero. Imagine for simplicity that there are no zero for the moment. So imagine that the game is fair, but we can work with unfair games by transforming them into fair games. There is a trick to create martingales from unfair games. So there is a trick, but for the moment, let's say that we bet, so the red wins with probability 1/2, the black color wins with probability 1/2. And let's imagine that initially I have $100, and every moment of time, every moment of time, I bet $1 on red. Every moment of time, I bet $1 on red color. And I quit. So tau is so x0 is my fortune. Yeah, x0 is 100. So xn plus 1 is xn plus my the change. Let's say w n plus 1. Wn plus 1 is either plus 1 with probability 1/2, either minus 1 with probability 1/2. And the stopping time is the following. I stop when one of two conditions is satisfied. Either I've lost all my money, either xt is 0, or xt is 120, or maybe no, 220. Okay, so that is my strategy, my stopping time. I will quit the casino when I have no money or when I have $220. I start initially with $100 and I will quit the game when I will either win $220 or I have no money to play. So that's my stopping time. The moment of time when I quit the game. And my question are, first question, what is the probability that I will win the game? So when I will quit in the money, so that's the probability I will quit the game with $220. And question B is the expected duration of this game. I have two questions. I have a fair game. I bet on the red color. Red color appears with probability 1/2. So with probability 1/2, I lose $1. With probability 1/2, I get $1 more. Obviously, that this is a martingale. My xn, yeah, my fortune is a martingale. Expected value of xn plus 1 given xn is xn plus 1/2 times plus 1 plus 1/2 times minus 1, and obviously that's xn. Yeah, obviously this game is a martingale. My fortune in this game doesn't change on average. Yeah. Tau is a stopping time. I don't look into the future with this tau. Tau has no such ideas like quit the game before you lose $1 or quit the game before you lose $2 in a row. Yeah, that would transform the fair game into favorable game, such forbidden strategies. But these strategies are forbidden by the requirement of the Dupes theorem and by real life. Yeah, so the event that you quit before or at time moment n you should be able to describe this event in terms of x1, xn minus 1. Yeah, if you remember, this sigma algebra is all the events you can state, you can describe, you can phrase in terms of these random variables. Okay, now let's move to the solution. Okay, let's think a little bit. The solution is very fast if you understand the idea of Dupes theorem that you can't make money on a favorable game. So what are the possible values of x tau? X tau can either be 0 or 220. So these are possible values of x tau. Yeah, because I quit when I have $0 or when I have $220. So there are only two values, and this probability p is unknown, and this is 1 minus p. So from one point of view, expected value of x tau is 0 times 1 minus p plus 220 times p. But Dup's theorem says you can't make money on average. Yeah, so it may happen that you make money, but on average you can't make money on average if you play a favorable game. So basically it says that expected value of x tau, xn is a martingale, yeah, n is a martingale here, and hence expected value of x tau is equal to x0, but x0 is 100. I start with $100 initially. Hence, 220 times p is 100. Hence, p is 100 over 220. And without considering all possible events, how may I win 200? Because there are many different ways, different histories of the game to have $220. Yeah. So just I quickly obtained the answer from qualitative idea that we can't make money on average if we play a favorable game. So expected value of my final fortune is equal to my initial fortune. Okay, now with what is expected value of tau. Here we needed to be a little bit more creative. We need to create a martingale. If we look at our previous example with monkeys, the success was how we mastered to calculate expected value of tau. What was the reason we succeeded? We succeeded because we had n inside our martingale. So now we will create a martingale which has n in the formula. We will have a martingale that has n inside the formula. Okay, for the point B, we need to be more creative. And we will consider the following process. Yn will be xn, I think xn minus 100 squared minus n. Yeah, let's consider this process. Okay, let's consider this process. That's a very strange process, but it has n inside. Okay, what is the next value of yn plus 1, given that you know past information, you know all past values of y? What is the next value? Yeah. Okay. So if you know, let's plug in the formula for yn plus 1 inside. That's xn plus 1 minus 100 squared minus n plus 1 given my information and given my information. But if I know all values of y, I know values of x. So if I know the value of y, I know basically the value of x. Or even yeah. Let's work directly with sigma algebras. That would be easier. Fn. Fn is a sigma algebra generated by the sequence, by the flow of the game. Yeah, I just observe the results of every bet. Hence, what do I have here? I have xn plus wn plus 1 minus maybe it will be xn plus 1 squared minus 2xn plus 1 times 100 minus n plus 1 given fn, oops, plus 100 squared, yeah, given fn. So what do I have here? I have here expected value of xn squared plus 2xn times wn plus 1 plus wn plus 1 squared minus 2xn plus 1 times 100 minus n plus 1 plus 100 squared. Yeah. And I think that's all. I will cancel everything now. How much time do we have? Oh, we have -3 minutes. Okay, let's finish quickly. Okay. Xn plus 1, we know. It's known at time n, so it's xn squared. Xn is known, so that's 2xn times expected value of wn plus 1 given fn. So wn squared is just 1, because wn is plus 1 or minus 1, so we get plus 1. Xn is a martingale, so we have minus 2xn times 100. We have minus n plus 1, that's a constant, plus 100 squared. Okay. Wn plus 1, that's either plus 1 or minus 1 with equal probabilities. So this value is 0. And that's xn squared minus 2xn times 100 minus n plus, or maybe plus 100 squared minus n. And I see that xn minus 100 squared minus n, that's yn. So we have proven that this artificially constructed process is a martingale. Expected value of yn plus 1 given fn is equal to its current value. So that's a martingale. Yn is a martingale. And if yn is a martingale, so I can apply Dup's theorem. Dup's theorem says expected value of y tau is y0. Y0 is x0 minus 100 squared minus 0. It's 0. And hence expected value of y tau is expected value of x tau minus 100 squared minus tau, and that should be 0. And hence expected value of tau, the goal we have, is expected value of x tau minus 100 squared, and with probability with probability P, this is equal to 220 minus 100. With probability 1 minus P, it's equal to 0 minus 100. And P is equal to 100 over 220. And hence, we have found expected value of tau. We are happy. Expected value of tau. It happens to be okay. That's 100 over 220 times 110 squared plus 110 squared over 220. Oh, sorry, 120 over 220 times 100 squared. So that's expected value of tau. And I hope with these three examples, I have shown you how martingales are applied to solving questions in probability theory. So I understand that these examples are rather complicated, and in the home assignment, you will have less complicated examples. But let's consider that these examples like a masterclass, like you have an idea what is done in real life, when martingales are applied in real life. We create martingales, we apply the idea that you can't win the fair game on average, your average final welfare in a fair game is equal to your initial welfare. And this simple idea, very intuitive, can help us to solve rather complicated problem. If you try to answer this question without martingales, that would be much more difficult. Okay, thank you everyone. Sorry for being late, but I would prefer to finish the third example. That's all for today. If you have any questions, just don't be shy.
Thank you very much for your lecture. Could you please show how to solve second exercise from midterm about moment generating function? It seemed really interesting because it feels like there needs a integral definition, not an infinite sum definition to solve it.
Okay, let's look at the second problem. Let me open, because I don't remember. Just a moment, I will open it. Yeah, I see. Okay, there are two. So first, the problem number 2 from the exam. Okay, so first let's work with point C. So point C is, I think, more or less obvious. It says what are the rule, or what are the probabilistic meaning of second derivative of the moment generating function minus first derivative squared. But if you remember, so point C is just, if you remember what is the main use of moment generating function, so you get points just for free. You can say that is expected value of s squared, that is expected value of s in brackets squared, and hence that is the variance of s. Okay, the probabilistic meaning of such a value, that the variance of s. Okay, so we've got some points just for free. Now let's look. Let's calculate the conditional moment generating function. Okay, let's look at the conditional moment generating function. Okay, we have n is fixed in point A. We have n that is fixed. Yeah, in point A, everything says n is fixed. So for the moment, to solve point A, I ignore completely the information about the distribution of n. In the point A, n is fixed, and hence, oh yeah, it would be better to publish it. Sorry. Can I copy it? Yeah. I will drop it in the chat. Just a moment. Pa-pa-pum. Here we are. Let's. Yeah, I've dropped the second problem. Okay. So in the point A, n is fixed because it has calculate conditional expected value when n is fixed. Calculate conditional moment generating function, n is fixed. So if n is fixed, I ignore completely the information about probability mass function of n is equal to. So I ignore this information. We fix n. So n is like a constant.
And we will get like some function that is written in terms of n, right?
Yeah. We will get a function that is written in terms of n. And when we will solve the point B, we will recall that n is a random variable. Yeah, exactly. Okay, so what is expected value of s given n? Expected value of x1 plus x2 plus plus xn given n. Once again, n is fixed, so it's n times expected value of x1. What is the value of x1? X1 has uniform distribution from 0 to 1, and hence it's n times 1 over 2. Okay?
Sorry, but why we made this like transition that it's equal to n times expected value?
N is fixed. What
yes,
does it mean? Fixed n.
So
N is constant. You ignore the information. So what is the idea of conditional expected value? Fix. Imagine that you know n.
yes, I get it. And by the way, wouldn't it be easier to find a moment generating function first and then just like take a derivative and equal
Yes,
t to 0?
you can follow this strategy, but I show you two strategies. Yes, you can.
Okay, thank you very much.
Yes, you can. That's a possible strategy, but I show you the technique. So you can calculate expected value of s given n directly, or you can use moment generating function that is, okay, we will find it. What is a moment generating function of s given at u? So what is it? Once again, we fix n. What does it mean conditioning on n? Fix n. Think that is a known parameter. Okay, if n is a known parameter, we calculate moment generating function. So we calculate expected value of exponent of s times u, given that you know n. Okay, that's exponent of x1 times u plus x2 times u plus xn times u given n. Yeah.
What is the formula that describes that we can do such a transition like in first row? So the not intuitive part is why we can just put that this mass expectation is given n.
There's a definition. There's a definition. What is the definition of conditional moment generating function? You fix n.
Oh, I never seen a definition of conditional moment generating function, only of just moment generating function. Okay, I will take in mind.
No. I have presented it during one practice. I'm sure.
Okay, I trust you. During practice, like a seminar.
But it's practice for every group, so that's fair. That would be
Okay,
unfair
but
to present it during a class for a particular group, but that's not the case.
so So it was on lecture?
Yeah, so during practice, so you have 2 lectures, like on Fridays, on Saturdays, so that's fair. Yeah, everyone has
okay.
the same information.
Oh, by the way, I wanted to ask, why do we have like 2 lectures? So, as I understand, like Saturday's lecture is with Piotr Lukichenko.
That's the design of the course. Yes, you may blame it. Yeah, there are many pro and many cons. The idea that math is difficult, basically, that's all.
Okay. No, I
So
actually like this
we have,
decision.
so basically math is difficult and we have many goals. We decided to, so we cover two external exams, and we would like to present stochastic calculus and time series modeling. So basically we have too many goals, and that's difficult. We have 2 external exams, and we have time series
Only one
forecasting,
course.
and we have stochastic calculus in mind. So if we omit, let's say stochastic calculus, if we omit time series forecasting and we focus on just on external exams, I think 1 lecture is enough, plus class, but it would be it would decrease the quality of your education if we omit the time series forecasting and stochastic calculus.
Okay, thank you very much.
Very
By the way,
okay.
will you be teaching time series in the next half year?
I don't know yet.
Okay.
Okay, I don't know. Okay, so that's a conditional moment generating function. Okay. We have that's expected value of the exponent of x1u given times exponent of x1u times exponent x2u times exponent of xnu given n. Hence, what do we have here? As we fix n, x1, x2 are independent, so we can say that exponent x1u given n, so that's just to the power n. Yeah, we have n similar terms. What is this value? That's an integral from 0 to 1, exponent of xu times 1, the PDF probability density function of x1 du power n. Okay, what do we have here? We have, so we need to integrate. That's very awful integral. We have exponent of xu divided by, oops, sorry, dx. I'm wrong here. U is a parameter, dx. Divided by ux ranging from 0 to 1, and this goes to
one
the
is
power n.
one is
Sorry?
a PDF of one is PDF of x1.
Yeah, x1 is uniform from 0 to 1.
Yes, well, but PDF of
the PDF
well, like
probability density function.
it's like 1 over b minus a, right?
Yeah, exactly.
Yes. Okay.
But b is 1 here, a is 0 here. Yeah. Okay, so we have exponent of u minus 1 divided by u power n. And now comes, so we have solved a. And b, the moment generating function unconditional, that's expected value of conditional expected value. exponent of SU given n. So we use the tower property of conditional expected value, tower property.
So here n is not fixed already.
Yeah, now we relax. So now we will use the distribution of n. Yeah.
And well, can we just forget about n? We can't, right? Because
No.
S is dependent on n.
Yeah, and now we will have a probability that n is equal to 1 multiplied by exponent u minus 1 over u power 1 plus probability that n is equal to 2 times exponent of u minus 1 divided by u squared and so on. So now we consider n as a random variable. So when n is equal to 1, that happens with probability n equal to 1, and the value, the power will be equal to 1. When n is equal to 2, that happens with probability that n is equal to 2, and that's the squared value of exponent u minus 1 over u.
Sorry,
Okay?
could you please clarify about like the tower property? How we like went from definition of MJF to
What is the definition of MJF? That's expected value of the exponent of SU.
Yes.
And we know the rule that the expected value of an elephant is an expected value of an elephant given any hedgehog. Yeah. So that's the tower property. You can put anything instead of elephant. Instead of elephant, I have this is an elephant. Yeah. And this n is a hedgehog. Yeah.
Okay, thank you very much.
So that's the general rule. You can put anything, any random variable you like.
But it has to be independent with x.
No, that's the general rule. You can put anything here. It may be dependent. That doesn't matter. That's the power. That the mighty. Why it's so useful. You can put anything there. Dependent variables. That's okay. So that's the power of this formula. You can choose what to put inside. So you need to calculate the value of an elephant, and you can use hedgehog in such a way to make all calculations as simple as possible. That's the power of a formula. So you're not obliged to choose the hedgehog independently of the elephant. So that's the powerful. You are asked to calculate this, and you say, no, I will calculate this in a way I like. I will choose any random variable as a hedgehog, and then I need to calculate audience. So that's the power of conditioning. You use this trick is called conditioning, and you condition in such a way to make all the calculations as simple as possible. Okay, now let's move on. We fixed n, and we average over all possible values of n. So let's call this, so what is the probability that n is equal to 1? According to the text, the probability that n is equal to 1 is 7 times 7 over 3 times 0, 3 power 1 times alpha power 1. Yeah.
Just a second. How we got like expected value of u minus 1 divided by u to some power? What from which formula do we get this like
So
summand?
that's a random variable.
Like yes, we just obtained it. Yes, thank you very much.
Oh, that's the value of a random variable times probability. Value of a random variable times probability. 7 over 3 times 0, 1, 0, 3 power 2 times alpha 2, 0, 3 times alpha 3, and we see that's the geometric series, yeah. So it's kind of b1 over 1 minus q, yeah, if you remember the middle school, yeah. I think that's and hence we got b1 is this one, 703 times 0, 3, 1 alpha 1 divided by 1 minus every time it's multiplied by 0, 3 alpha. Hence we can divide by alpha, and we got 0, 7 divided by 1 over alpha minus 0, 3, and 1 over alpha it's just 0, 7 u over exponent of u minus 1 minus 0, 3. Yoo-hoo. That's the moment generating function. And you can take all the derivatives and so on. So that's the moment generating function.
Such a crazy task for a midterm, actually.
Okay.
With a really crazy concept in mind, but a nice problem. So thank you very much for explaining this. And what is the intuition that like we choose? So for n equals 1, we will like raise our moment generating function conditional to this power n.
The idea why moment generating function are useful.
Wait, it's just by the formula from A, right?
Why they are useful? Because they behave well when we apply them to sums. So the main good property of moment generating functions. So if you have the sum of random variables, and these random variables are independent, and you calculate the moment generating function of a sum, so that's a moment generating function of x times moment generating function of y times moment generating function of z. Yeah, so the main
yes.
property. So basically, as we have s equal to x1 plus x2 plus xn, imagine n is fixed. N is fixed. Yeah. So hence moment generating function of s when n is fixed, n is equal to n. Yeah, let's say fix it. It will be moment generating function of x1 times moment generating function of x2 times moment generating function of xn, but they are equal. All these variables x1, x2, and so on are distributed according to the uniform law. So hence it will be moment generating function of x1 power n. And the only difference is when we should now relax the simplifying assumption. So point A basically is just this idea. And in point B, we relax this assumption and we say that ms given n of u, now that's a random variable. That's mx1 of u power n. Now this is a random variable. This is a random variable. And basically we are calculating the expected value to get the moment generating function of s.
Yeah, wanted to say that I really like the idea of this moment generating function. It seems very beautiful, this idea of like taking derivatives and equating some helpful variable to zero to use like a Taylor expansion for like a package of functions.
Yeah, package, of constants. Yeah, package of interesting constants. Yeah, I agree with you. That's very useful.
And
Okay.
sorry, can I ask the last, like, pretty fast question?
Yeah.
I wanted to ask, like, what are applications of stochastic processes? Because, like, our program is called application, no, like, прикладной анализ данных, but it's rarely spoken about how to apply these mathematical interesting concepts that we get on your lectures or other one lectures.
Okay, we will in the next, I think, 4 weeks, we will go to stochastic calculus and we will price European options using these techniques. So, for example, you can price European options, and you can then apply to the master program in quantitative finance, and so the guys who work in quantitative finance, they use stochastic calculus to price derivatives. So we will give you the introduction to this field of pricing options, for example.
Mm-hmm.
And after the new year, we will discuss time series forecasting. That's, I think, the application of time series forecasting is more or less obvious. Yeah.
Yes.
So.
Okay, thank you very much for such a clear and complete explanation.
Okay, see you next time.
See you next time.
Yeah, bye-bye.
Have a nice weekend. Goodbye.